Guys, this is Dr. J here, and in this short video we will talk about chirality of carbohydrates. And please note that I also have a video titled Stereochemistry at Tetrahedral Centers part 1. So this that particular video is actually more detailed on the term chirality. So if you want a more broader understanding to the chemical term called chirality, I highly recommend that you guys watch the video titled Stereochemistry at Tetrahedral Centers Part 1. So once again, this short video is mostly focused on carbohydrates chirality, and this video is intended for CHM 105, which is Introduction to Organic Chemistry. Alright, so as I mentioned earlier, okay, we have talked about the term called isomers before. Okay, so if I ask you what are isomers, okay, you already know that isomers are basically different chemical compounds with same chemical formula, right? So basically they have the number of carbons, hydrogens and any other atoms in same amounts, right? So they basically have the same chemical formula, but usually isomers have different arrangement of atoms. Isomers have different arrangement of atoms. Same chemical formula, different arrangement of atoms. And when talking about these isomers, there are two primary kinds of isomers: constitutional isomers and stereoisomers. Constitutional isomers and stereoisomers. And in fact, the chirality falls under stereoisomers. Chirality, which we are going to talk about in this chapter, is going to fall under stereoisomers. And by now we are actually very familiar with the other type of isomers, which we call structural or constitutional isomers. Okay, we are already very familiar with constitutional or structural isomers. So constitutional isomers are known as chemical compounds, once again with the same chemical formula, but atoms are connected differently, right? So by looking at the structure of the molecule, okay, if you take a look at this C2H6O chemical formula, these ethanol and dimethyl ether, these are two different isomers. Why? Because they both have the same chemical formula, but when you take a look at this structure, you can easily see that they are different molecules. Why? Because ethanol has an OH group, oxygen and a hydrogen together, and in this diethyl ether, even though it has the same chemical formula of ethanol, it does not have that OH group. It has an oxygen sandwiched between two carbons, and we learned that this dimethyl ether falls under the chemical group or chemical compounds called ethers, okay, and ethanol falls under alcohols. Here's the thing, even though they have the same chemical formula, by looking at the structure, we can easily say that they are different. Why? Because they are different structural isomers. The atoms are connected differently. And one such example is given below, okay, propanol and propanone, okay, both these have the same chemical formula. One is an aldehyde, this one right here is an aldehyde. This one is a ketone. They are also isomers, and they also falls under structural isomers. The differences are obvious by looking at the structure, because their structure is different, right? Their structure is different. Atoms are connected differently. And we also learned another group of isomers called stereoisomers. Stereoisomers. So basically stereoisomers also have the same identical molecular formula, okay, but they are not structural isomers. Okay, if you just write the structure, you may not see the differences in the two compounds, two isomers, very easily. Okay, why? Because stereoisomers usually have the same connectivity of atoms, okay, same connectivity of atoms. That means each carbon is connected to the same number of hydrogens or any other atoms. So the functional groups will be the same. The skeletal formula will be similar. Okay, so the thing about stereoisomers are, even though their structure looks similar, okay, their atoms are oriented differently in space. So basically, if you want to understand stereoisomers, you have to look at the spatial arrangement of atoms. So in other words, you have to look at the molecule in 3D space. Okay, so you have to take a look at the molecule in 3D space, and we already talked about one such group of stereoisomers called geometric isomers. Okay, or in other words, you may be more familiar with cis-trans isomers. Okay, you may be more familiar with cis-trans isomers. So we learned about cis-trans isomers when we talk about alkenes, right? We talked about cis-trans isomers when we talk about alkenes. So they fall under stereoisomers. They fall under stereoisomers. However, the group of isomers that we are going to talk about are different from cis-trans isomers. They are different from cis-trans isomers, and these isomers are known as optical isomers. The chiral compounds or the stereoisomers that we are going to talk about today are called optical isomers. Basically, these optical isomers are mirror image molecules. Okay, so these optical isomers are mirror image molecules. That is a very important word to remember. These optical isomers are mirror image molecules. Okay, so these two molecules or these two isomers look almost identical because they are like mirror images, right? You take your left hand in front of a mirror, and then you see basically the reflection of your left hand. So it should be identical to your hand, right? So these isomers are also looks very similar. Why? Because they are mirror images of each other. They are mirror images of each other. But however, even though they have the same chemical formula, the same connectivity of atoms, even though they are mirror images of each other, you can't put them in the same 3D space. Okay, you can't put them in the same 3D space. You cannot put them in the same 3D space. Okay, or the technical word for that is non-superimposable. Cannot occupy the same 3D space. So what are optical isomers? They are basically mirror image molecules. Okay, they are basically mirror image molecules, but they are non-superimposable. They are non-superimposable. So these mirror image molecules that are non-superimposable can also be called as chiral compounds. Okay, chiral compounds. All right, so as an example, okay, so here is how this is a really good example actually. Take your right hand, okay, go in front of a mirror and then look at the mirror image of your right hand. So that mirror image looks very similar to your left hand, right? So take your right hand out and then put it in front of your right hand. I mean, they look basically mirror images to each other, right? So when you put your right hand in front of a mirror, you don't see your right hand. In fact, you see something similar to your left hand. So when you try to put the two hands on the same 3D space, you're trying to superimpose your thumb and the ring finger and all the fingers on top of each other, and you will realize that you can never put them in the same 3D space. Fingers will offset, right? So in your left hand side, the thumb will be on one side and the right hand side will have the thumb on the other side, right? So you can never put your left hand on the same 3D space as the right hand. Okay, so basically your left hand and right hand are mirror images, but they are non-superimposable. They are non-superimposable, right? So you can say that they are chiral, right? So, but of course, I mean, chiral term is used for mirror image molecules, but basically you understand the term, right? So even though your left hand and right hand looks identical, you can never put the gloves that is supposed to be a left hand gloves on a right hand side, right? So they are not going to occupy the same 3D space. Okay, so that is what chiral means. Okay, so if the mirror images are identical, then they are going to be superimposable. So those molecules are known as achiral. So the opposite word for chiral is called achiral. Okay, achiral means mirror image molecules that can be superimposed. Achiral. Okay, all right. So I have some objects from your textbook. Okay, so in these 4 examples, we can actually learn these 2 terms called chiral and achiral. Okay, so of course, in these examples, each example will have 2 objects. It could be a glove or a baseball bat. Okay, and the mirror image of the same thing. Okay, so sometimes these objects could be superimposable. You can put them in the same 3D space. Sometimes you cannot. Okay, as an example, the 2 blouses, even though they look identical, one will be suitable for the left hand, the other one will be suitable for the right hand. So even though they are identical or mirror images of each other, okay, the correct word is mirror images, even though these blouses are mirror images of each other, they will be non-superimposable. So you can say that these 2 blouses are chiral. These 2 blouses are chiral. But the baseball bats right here, they are mirror images of each other. So if you put a mirror in between, you will see the other thing, right? So they are mirror images, and also they can be superimposed. You can put the 2 bats in the same 3D space. So we call it achiral. The 2 glasses, once again, they are mirror images of each other, but you can put the 2 in the same 3D space. So that is an achiral molecule. And this pair of shoes, they are also mirror images of each other, but you cannot put, the left shoe doesn't fit your right leg, right? So like that, even though they are mirror images of each other, the 2 shoes are mirror images of each other, okay, they will not occupy the same 3D space. So those 2 shoes are chiral. So now you understand it, right? So the term chiral is used for 2 mirror image molecules that are non-superimposable, that do not occupy the same 3D space. The word achiral uses for 2 mirror image molecules that can be superimposed on the same 3D space. Okay, so that is the difference. But let's apply this knowledge into molecules. Okay, molecules. Okay, so once again, if you want to apply this theory into molecules, you might think that, okay, now I need to know the structure of the molecule, or in other words, now I need to know the 3D arrangement of the molecule, right? So then I need to visualize this molecule, and then I need to visualize the mirror image molecule of that molecule, and then I have to try to put them in the same 3D space. Your brain will explode, right? If the molecule is too complicated, visualizing a molecule in 3D space is hard enough, but now you have to visualize the same molecule with the mirror image, and then you have to put them in the same 3D space. So it will be very difficult, right? But no, don't worry. There is a shortcut. Okay, so rather than trying to find the mirror image and trying to put them in the same 3D space, you can actually have a shortcut. Okay, you can have a shortcut. All right, so this shortcut is actually, you have to find a carbon atom in your molecule. And this carbon atom should be an sp3 hybridized carbon. It should be a sp3 hybridized carbon. That means it only should have single bonds. Okay, find an sp3 hybridized carbon. That means carbon with only single bonds. Okay, and if this carbon has 4 different groups attached, A, B, C, D. Okay, if this carbon has 4 different groups attached, okay, that carbon is considered to be a chiral center. So this carbon is identified as a chiral center. The thing about these chiral centers is that when you have a chiral center, the molecule will be a chiral molecule. So if a molecule has a chiral center, that molecule tend to be a chiral molecule, which means that molecule will have, so this whole molecule will have a mirror image molecule that will be non-superimposable with this molecule. Okay, let's take an example. All right, let me take a new one. There you go. Alright, so I'm going to draw a molecule now. Okay, so let's say I have a molecule like this. Right, here is our molecule, and then we have a mirror. Okay, so we are trying to get the mirror image, but before getting the mirror image, let's do the trick that we just learned. Let's do the trick that we learned. Find a carbon. Okay, find a carbon. So this molecule has 2 carbons. Here is carbon number 1, here is carbon number 2. Okay, so both these carbons are actually sp3 hybridized. How do I know that they are sp3 hybridized? Because they only have single bonds, right? They only have single bonds. We know that. Okay, both carbons are sp3 hybridized. Now we have to find a carbon that has 4 different groups attached. If you take this CH3 group, okay, does it have 4 different groups attached? No, it has 3 hydrogens. So that's the same atom, right? So this carbon is not a chiral center. This carbon is not a chiral center. Take a look at this central carbon. There's a reason why I drew it in 3D. Okay. So by the way, this wedge means that bond is coming out of the plane. This dash means it is going into the plane. Okay. And the straight lines, those bonds are actually on the plane of the screen. Okay, so this carbon right here has 4 different groups attached, right? This carbon right here has 4 different groups attached. If you label the 4 groups, okay, the first group is OH, the second group is Cl, third group is what? CH3, and the fourth group is what? Hydrogen. So this carbon right here has 4 different groups attached. That much is clear. If a carbon has 4 different groups attached, okay, then we say that carbon is a chiral center. If a molecule has a chiral center, that molecule becomes a chiral molecule. A chiral molecule, which means it will have a mirror image molecule. It will have a mirror image molecule that is non-superimposable. That is non-superimposable. So here is the mirror image molecule. Okay. Here is the mirror image molecule, and this mirror image molecule will not be superimposable with each other. Okay, so we call these 2 molecules chiral. Okay, so these 2 molecules are chiral, but you don't need to write any of these mirror images. As long as you have a carbon, that has 4 different groups attached, we know that the carbon is a chiral center, or chiral carbons. Therefore, this whole molecule is a chiral molecule, which means it has a non-superimposable mirror image molecule. Okay, non-superimposable mirror image molecule. Alright, so I spent like 20 minutes explaining it, but of course the other video will be much more detailed. Okay, so if you want to watch the other video, go ahead and do it, but the amount of explanation that I have given you is, I think, enough for this level. Alright, so here is another example. I have a molecule, okay, this black dot is the carbon, and then it has 4 different groups attached. So we know that this carbon right here is a chiral carbon, making this whole molecule a chiral molecule, right? Which means its mirror image molecule, which is this one, is non-superimposable to each other. So these are optical isomers, or we call them enantiomers. Remember the term, okay? So when stereoisomers cannot be superimposed, okay, they are called enantiomers. Remember the word, okay? When you have two mirror image molecules that cannot be superimposed, that cannot be placed in the same 3D space, we call them enantiomers. All right, so the problem is, okay, so any carbon that has less than 4 different groups. In here, in this molecule, I have 2 identical groups, right? So this carbon do not have 4 different groups attached. If that is the case, the mirror image molecule is this one. So once you have the mirror image, you can always rotate it in a certain way so that you will obtain the previous molecule. You will obtain the previous molecule. So therefore, those mirror image molecules will superimpose with each other. So we call them achiral. We call them achiral. All right. So identify each as a chiral or achiral compound. So you might want to pause the video and then write C or A in front of the compound. C for chiral, A for achiral. All right. Let's do compound number A. Of course, you have 4 different carbons, okay? And if you take a look at this middle carbon right here, it has 4 different groups attached. It has 4 different groups attached. So this one right here is certainly chiral. This one right here is certainly chiral, okay? And then take a look at the second compound. Here it has 2 carbons. Of course, this CH3 group is useless because it has 3 of the same group attached. If you take a look at this middle carbon, it has 1, 2, 3. Okay, only 3 different groups attached. So if you only have 3 different groups attached, that is not chiral. Okay, you have to have 4 different groups attached. So this one right here is achiral. Okay, and let's do the fourth compound. Very easy now. Okay, this CH3 group will not qualify even though it is a single bonded carbon. It has 3 of the same groups attached. So that is not a chiral center. Look at this central carbon. It has 4 different groups attached. Chlorine, hydrogen, bromine and CH3. 4 different groups attached. So this one right here is chiral. This one right here is chiral. So A is chiral, B is achiral, C is chiral. Alright, so we spent 22 minutes explaining what is chirality and all those kind of things. But hey, for your exam, let's say for this level, all you need to do is find out a carbon that contains 4 different groups attached. And if you find a carbon like that, that compound will become a chiral compound, which means that compound will have a mirror image molecule that is non-superimposable with each other. So we call them chiral molecules. All right, that is all you need to do. Need to know, okay? And then next part of this video involves drawing 3-dimensional molecules in 2D. Of course, you know, sp3 hybridized carbons or carbons with only single bonds. Their geometry is what? Their geometry is tetrahedral. Their geometry is tetrahedral. So sp3 hybridized carbons basically have a structure like this. A bond coming out and bond going in, right? So this structure we call it tetrahedral. So if you have to draw these molecules in 3D all the time, or at least, you know, 2D using these wedges and dashes, it is time consuming. It is time consuming, right? So we need to learn how to draw these 3D tetrahedral shapes in 2D. Okay, one way to do this easily is called Fischer projections. Okay, Fischer projections basically is a 2-dimensional representation of a 3-dimensional molecule. Okay, Fischer projections are a representation of 3-dimensional molecules in 2D. Okay, so it only has lines. Okay, lines and atomic labels. So Fischer projections, I like to call them butterfly projections. Okay, I like to call them butterfly projections. So if you imagine a flower, okay, so let's let's have a nice little flower like this. Okay, so oh, that went bad. Anyway, so and here is a butterfly. Okay, and then here is the wings. All right, pardon my really bad drawing habits. Okay, but anyway, so you get the point, right? So this is how a butterfly looks like. So Fischer projections, I like to call them butterfly projections because it basically resembles a butterfly. Okay, it basically resembles a butterfly. Usually in face-to-face classes I demonstrate it, okay, me being a butterfly, and then I show how it happens. But anyway, I try to do it on paper as well as I can. Okay, but for these Fischer projections, you basically put the most highly oxidized carbon at the top. In other words, you basically put the carbonyl group on top, okay, because we are going to have aldehyde or ketones, right? So put the aldehyde or ketone group on top. That is the most important thing. Okay, that will be the top carbon. Okay, and then comes the butterfly. Okay, so basically if you imagine a tetrahedral shape, it looks like this, right? It looks like this. It has two bonds in the same plane, and then you have a wedge and a dash. Okay, so if you have a tetrahedral shape, I want you to bring it to you now. Okay, so this same shape you can draw it like a butterfly. Okay, let's say here's the head of the butterfly, which is basically folded towards the flower. Okay, so this is our flower. Okay, this is our flower, and then here is the axis. Okay, so head part is folded in, excuse me, and then the tail part of butterflies have that thing, the ball like thing, I don't know the biological names. Anyway, so that is also folded towards the flower, right? So the top bond and the bottom bond, they are both folded into the flower. Okay, so the flower is, let's say, inside the screen. Okay, so the top bond, let's call it A, so it is going into the plane, and then let's call this the B. Okay, that is also going into the plane. Okay, so this is the central carbon, by the way. So this body is your central carbon, and then this carbon also has what? Two wings, right? One here, and then the other one is actually, this is coming out. Okay, the other one is going in. Okay, so the wings are like this. Okay, so the tetrahedral shape, okay, you can put it like this. Two bonds are coming out of the plane. Okay, the wedges are what? They're coming out. These are coming out, and the dashes, they are going in. They're going in. Okay, these are going in. All right, so basically this looks like a butterfly. A and B is like the butterfly's head and tail. They are folded into the flower. They are folded into the flower, and the wings, they are going out of the flower, and actually they are kind of like coming out of the flower, right? So they are coming out of the plane. Okay, so this looks like a butterfly, right? I mean, at least. All right, so basically in Fischer projections, what they say is the vertical bonds. Okay, the vertical bonds are going into the plane, and the horizontal bonds are coming out of the plane. Okay, so these ones are coming out, the wings. Okay, these are coming out, and the head and tail, they're going in. They're going in. So rather than drawing these wedges and dashes, you can easily draw a tetrahedral carbon using a cross. You can easily draw a tetrahedral carbon using a cross. Okay, you can easily draw a tetrahedral carbon using a cross. And of course, the middle part is your carbon, and it has four bonds, and the vertical bonds. Okay, vertical bonds are actually going into the plane. This is also dash line, and then the horizontal bonds are coming out. Horizontal bonds are coming out. Horizontal lines, okay, they are coming out, wedges. So vertical bonds, they are going in. Okay, going in. I think I have a better image in the next slide. So this is, I mean your text, this is actually from your textbook, but it does a very poor job actually. I mean, dash lines should be like this, okay? They have some certain depth. But anyway, so this is an example, okay? So here is our butterfly kind of thing, okay? OH and hydrogen, they are coming towards your face, okay? Let's say you are looking at the screen now, okay? So OH and hydrogen, they are coming towards your face. So it's like, you're looking at a butterfly and the wings are coming out of the body, right? This carbon right here is the center where the wings are attached. So they are coming towards you. You're looking at the butterfly, right? And the head and the tail, they are folded in. So they are basically going into our screen, okay? They are going into our screen. So rather than drawing all the dashes and wedges, you can basically simply draw it as a cross. Draw it as a cross, and of course the horizontal bonds, OH and hydrogen, they are coming out, okay? So these are these wedges, okay? They are coming out of the plane, and then these dash lines, okay, the carbonyl group and the CH2OH, carbonyl group and CH2OH, they are going into the screen, or in fact the vertical bonds, they are going in. They're going in, okay? They are going in. That is all, guys. Okay, that is all. By the way, the molecule that you have here, okay, they are mirror image molecules, of course. And if you take a look at this middle carbon, it has 4 different groups attached, right? And these two are mirror images of each other. The left hand molecule is a mirror image of the right hand molecule. So you have a carbon with 4 different groups attached, and they are mirror image molecules. So they are chiral molecules, okay? They are chiral molecules. So in a chiral molecule, okay, identify the chiral center, okay? So this carbon is a chiral center. This carbon is the chiral center, right? So in a chiral carbon, if you have a hydrogen on the right hand side, it is opposite to having a hydrogen in the left hand side. Okay, so these two are mirror images without looking at a mirror, okay? We don't worry about the top bond and the bottom bond. Don't worry about the top bond and the bottom bond. They don't have any impact, okay? Top bond will always be the carbonyl group. Okay, identify the chiral carbon, okay? And then if the bond is coming, the hydrogen is in the right hand side here. And in here, the hydrogen will be in the left hand side. So they are definitely mirror images. They are definitely mirror images, okay? And here's the thing. So usually that is how you draw Fischer projections for carbohydrates. Your carbonyl group will always be on top, and then you look at the chiral centers, and that means the carbons with 4 different groups attached, okay? And those chiral centers will have 2 bonds that are different, okay, from the mirror image molecule, okay? That's it. And now let's talk about the isomers, right? Let's talk about the chiral isomers, right? Optical isomers. So in sugars, we have something called D and L notation. D and L notation. So this is how you assign isomer names, okay? D and L is used to assign isomers, okay, optical isomers to carbohydrates. To do this, you will basically figure out the bottommost chiral center. If you look at this molecule, okay, this one has 2 chiral centers. Here is the number 1 chiral carbon, here is the number 2 carbon. Okay, they are both chiral. Why? Because if you take a look at each of these carbons, they have 4 different groups attached, of course, right? So both 1 and 2 carbons are chiral carbons, but we focus on the second carbon. Why? Because it is the bottommost carbon, or in other words, we want to focus on the furthermost chiral carbon. Okay, chiral carbon furthest from the carbonyl group, which is what? Which is the second one. So you identify the furthermost chiral carbon or the lowest chiral carbon, and then you focus on the OH group. If the OH group is to the left hand side, hey, this is all you need to know, okay? You identify the bottommost chiral carbon, and if the OH group is to the left hand side, that is the L isomer. That will be the L isomer. If the OH group is to the right hand side, that is the D isomer. Okay. Let's say you didn't learn anything up to now that I just mentioned. This is all you need to know. Okay. Once you have a sugar molecule, okay, identify the lowest carbon that contains 4 different groups. Identify the lowest carbon that contains 4 different groups. This carbon does not count. Why? Because it has 2 hydrogens. That is the same group twice. So this carbon is not going to work. So identify the lowest carbon that has 4 different groups attached. Okay. So hydrogen, OH, CH2OH, and all this. Okay. So that's 4 different groups. Identify the lowest carbon and look at the OH group. If it is to the left hand side, that is the L isomer. If the OH group to the right hand side, that is the D isomer. That is all you need to know. Okay. That is D isomer. Let's see if you could do this. This study check asks you to indicate whether each pair is a mirror image that cannot be superimposed, or they're asking us whether they are enantiomers or not. Okay, no D and L, don't worry about it yet. Alright, so let's start. You might want to pause the video and come up with your own answer. Okay, alright, let's do this. Look at the 2 molecules that you have. Okay, look at this one. This carbon seems like it has 4 different groups attached. This carbon right here has 4 different groups attached. The hydrogen, the bromine, the CH3 and the CH2OH. All 4 are different. So that is a chiral carbon. And therefore the mirror image molecule should be non-superimposable. Okay, non-superimposable. So these are chiral. Alright, so look at B. Look at the carbon in the middle. And this one, both these carbons do not have 4 different groups attached. Okay, both these carbons. This carbon, no this carbon. Both these carbons have no 4 different groups attached. So they are achiral. Okay, that is how you do it. Let's go to the next study check. Alright, identify the following Fischer projections of aldose as L or D. This is easy. Okay. So we take a look at the structure and we identify all the chiral centers. 1, 2, 3, 4. All these 4 carbons have 4 different groups attached. And then out of these 4, highlight the bottommost one. This one is the bottommost one. Okay. So the bottommost or furthest carbon from the carbonyl group. Identify this. This is the carbon of interest. And look at the OH group. It is towards the right hand side. So this will be a D isomer. Look at this one. So this will be the bottommost chiral carbon. Okay, this will be the bottommost chiral carbon. Okay, and the OH group is to the left hand side. This will be L isomer. Okay. Alright, so identify the bottommost chiral carbon, the carbon with 4 different groups attached. Look at the OH group direction. If it is to the left hand side, that is L isomer. If it is to the right hand side, that is D isomer.